Yeah, thanks a lot again for having me give a talk about LINX, which stands for Light Isotope Nucleosynthesis with JAX. This is done in collaboration with Cara Giovanetti, Mariangela Lisanti, Siddharth Mishra Sharma, and Josh Ruderman. And if you are interested, you can take a look at the two papers that came out together with the code. Um, Actually, Elizabeth did a really good job going through a lot of statistical techniques and things like that. So that's really good because I'll be talking a lot about that in this talk. And then I will also go through a little bit about BBN itself and maybe cover some details that I missed earlier on. So the punchline is that, as we discussed in our lectures about BBN, we always want to compute elemental abundances as a function of time, and then we just want to know what the final abundance is, and then we want to compare that with observations. And this is just a video. Don't worry about the GitHub link. I'll show you the GitHub link in the end, and you'll get to run some of the notebooks that's part of the GitHub. And so I'm just showing you how all these isotope abundances evolve as a function of time as we change the baryon to photon ratio from very small values up to very large values. Okay, and the punchline is that really the main selling point of the code is that it's fast. So after a period of compilation, which maybe takes about a minute, you can do 50 evaluations in 12 seconds. So that's very rapid evaluation. And then to make this plot, to be honest, the code, making the plot took more time than actually running the code. And so it's a fast code. It's differentiable, which is something that I'll discuss a little bit later on. And we think it's written in a way that's kind of structured in a way that's friendly towards new physics applications. And we think that because now you have a fast code, you can hook it up with other CMB codes such as class, and that will kind of elevate the usual BBN analyses to the same level of statistical rigor as the CMB, which is something that I'll explain in the upcoming slides. Okay, so BBN in classic cosmology, I went through two examples of how to use BBN in lambda CDM and simple extensions to lambda CDM like n-effective. This is a summary of all of the current results from BBN in comparison with CMB. You'll see this Primart, Parthenopy, YOF labels here, which are three different ways to assemble the nuclear rates, something that I will also discuss later on in the talk. But you can see that it kind of jiggles the numbers a little bit, around a little bit. Although for delta n-effective, you're not very sensitive to nuclear rates anyway, so everybody kind of agrees on that number. Although actually it agrees in a way that is much less scattered than the CMB. So that we already discussed. But another thing that maybe I didn't discuss in the lecture is that having BBN gives you a way of obtaining omega B, and then that allows you to calibrate the size of the sound horizon. And using that information, you can calibrate the BAO feature, the distance to the BAO feature, and that allows you to do a CMB-free inference of H0. And this is from DesiDR2, which uses a combination of BAO plus BBN to determine H0, right? And you see that you get something like 68, H equals to 0.68. Two things I want to say about that. One is that it goes around all the CMB analyses, so you are free from CMB systematics if there happen to be any in CMB that's causing a low H0 value. And then the second thing I would say is that it still assumes lambda CDM, and it still assumes lambda CDM in the early universe before recombination. So it's not like this independent test just puts the Hubble tension to bed. It makes the same kinds of assumptions that go into a CMB inference for H0. Okay. New physics-wise, this was an example that I showed you, which is what happens when you have electromagnetically coupled dark matter. So if they can annihilate into E plus E minus, for example, then they would cause the BBN N effect. They will cause N effective to go below 3, and it will also change how BBN proceeds because of the entropy injection coming from annihilation. And so in very standard benchmark models for direct detection involving heavy dark photons, where people are interested in building kind of direct detection experiments to probe very light dark matter. Really, if the cross section is kind of, even if it's very, very small, 10 to the minus 41 centimeters square, which is way below all the constraints above, you can actually get limits from a combination of CMB and BBN. So it's a very powerful probe of light, so-called light dark matter. You might be surprised that like people are still interested in this mass range and all the way down to keV, even though there are already such strong constraints. And the standard law is that you can model build out of this. In other words, you can get creative enough to kind of lift these bounds. But to me, I find it extremely difficult. So I'm not fully convinced that you can build such models. Another thing you can do, for example, also, this is a little bit more exotic, but you can have, things like axions kind of modulating the neutron to neutron proton mass gap. And then that also affects how BBN proceeds. And then that sets some limit on the coupling of axions to nucleons as a function of axion mass, especially for very light axion masses. And these are just two examples, and there are many more things you can do with BBN. Okay, as a reminder, what do you need to do a BBN calculation? The first thing you need is you need to figure out how the neutrons freeze out, right? And so you need electroweak physics. In particular, you need to understand the diagram very well, and you need to be able to compute processes associated with this I think at this point at one loop level, that's good enough. You need the neutron decay lifetime to tell you how many neutrons decay after it freezes out and before the deuterium bottleneck ends, which happens around here. And then you need nuclear reaction rates. This is the 12, sort of the minimal set of nuclear reactions that you need to accurately predict the abundance of D and helium-4. And you need all of these reaction rates as a function of temperature. And then the two cosmological parameters that are of interest to us are the baryon abundance, omega b, or sometimes I'll call it the photon to baryon ratio. That's, it's the baryon to photon ratio, which are equivalent. Then there's the relativistic degrees of freedom, delta N effective, if we are talking about extensions to lambda CDM. All right, so putting all these things together, you can get these plots. Okay, a quick word about nuclear rates and uncertainties, which are the main uncertainties that that BBN is subject to. So you need this number here, sigma v, as a function of temperature. Sigma v just tells you the thermally average cross section of like two particles coming together and reacting. But the data that you have is the cross section as a function of energy. And this usually, if you look at plots in BBN literature, you have like, it always kind of looks something like this. You have like 10 to 20 data sets starting from the 50s all the way up till today, and they're all scattered all over the place. And you got to figure out how to do a fit to these data points, and then do a thermal average to get sigma v of t. And the main reason why you have disagreements between Prima at Parthenopy and YOF is how do you do this fit? Which data sets do you include? And the thermal average is kind of trivial, but basically these two things. How do you do the fit? Which data sets do you include? And that probably explains, it's kind of unclear, but I think that probably explains most of the differences. And then how do you parameterize the uncertainty associated with the fit? Obviously, many of these data points have error bars. And so you want to find a way to parameterize your uncertainty, of this number here. And usually the way that people do it is they just have one parameter per reaction, one which is going to be a nuisance parameter. And that's just going to adjust the normalization of sigma v of t. So after you do the fitting and then you do the thermal average, you get some curve as a function of temperature, and then you have one nuisance parameter that kind of allows you to rescale the whole thing up or down, okay? You can see that that's not really the right way to do it, but it's, that's pretty much how we do it currently. All right. So yeah, where it matters most. Yeah. And so this is just one of the reactions. This is one of the more important ones, and there are 11 others. Okay. Okay, so how does LINX do this? Um, this kind of layout, I mean, it's not anything special. Many other codes have the same layout as well. But the nice thing about BBN calculations, at least in like standard model, close to standard model applications, is that it kind of factorizes into figuring out how the background evolves. So the background is like, how does the electromagnetic energy density evolve with time? How does the neutrino temperature evolve with time, for example? And the part where you have to integrate the reaction rates. So that's the part where all the sigma v's come in and you have to do a integration over time. So you factorize the code. First, you calculate all the background quantities, including t, time as a function of scale factor, rho gamma as a function of scale factor, rho nu as a function of scale factor, and rho extra is the thing that contributes to n effective. You compute Hubble and things like that. So you do that in one module called background.py. You gotta tell the code, what is omega b h squared, what is the neutron decay lifetime, what are the nuclear rates, that nuisance parameter that controls the normalization of the nuclear rates, and if you want, you can put in delta n effective. Okay. Then you take all of the background quantities and you put it into the abundance module, and that's where all these differential equations are hiding. The nice thing that we did was you can specify, we have like a nice library of reactions. You can pick and choose which reactions you want, put them into something in nuclear.py, which has like which builds these networks, and then it actually looks at each reaction and cleverly kind of puts together this differential equation here. And then it passes it to abundances.py where the differential equation is integrated. Also, of course, you need to do all your weak rate calculations, which will determine how neutrons and protons go back and forth. And then at the end of the day, you get primordial abundances. This is quite standard. Many BBN codes do this. Okay. Okay, good. So let me discuss kind of the ideal way in which you should be doing a BBN calculation, right? So this is very, it resonates very well with what Elizabeth just went through in terms of large-scale structure, and the idea is very similar here. First, you have all of your inputs. In terms of lambda CDM or lambda CDM plus delta n effective, you have two parameters of interest if you're doing n effective as well. That's omega b and n effective. And then you have a bunch of parameters that are interesting, but you don't quite care about them in a cosmological setting. Things like tau n, which is the neutron decay lifetime, and then all of the rates, which remember we just control by one number. Okay? So in total, just for BBN alone, there are 14, at least 14, 14 parameters. If you want to include more reactions, you need to add more. Okay? Then you construct a likelihood, which is the probability of observing the data given your model, and these are at some model parameters. The likelihood is quite simple. We just use a Gaussian likelihood and compare, what you predicted from your BBN output, which is this d over h pred and yp pred, minus the observed d over h divided by the error bar squared of the observation. So that's your likelihood. And then you choose a prior. You choose a prior on omega b n effective and your nuisance parameters. And then you perform an MCMC to obtain the posterior distribution, which is the probability of your parameters given data. Okay? And then at the end of the day, you don't really care about these nuisance parameters. You want to marginalize over them, so you have to integrate them out. And then at the end of the day, you get the posterior on omega b and n effective. Okay? And like I said, the main systematic uncertainties are nuclear reaction rates, and you want to marginalize over them. Okay? And so LINX is kind of like the user-friendly way in which you can implement this whole procedure fully. And really, in terms of lambda CDM, the main advantage to this is that it's fast. Okay, so just now that I was talking just about BBN, Now the question is, how do you combine BBN and CMB, right? Because CMB also is sensitive to omega B and N-effective. So you could try to put those two um, things together and get a single posterior including both CMB and BBN data. You can do that. First, there's the BBN part of the flow, which is the same as what I described above. So everything in red is very similar, and it just goes into the BBN likelihood there. And then you need the CMB likelihood, right? And so the CMB likelihood, again, you have to pass the model parameters that you have up there as inputs into a Boltzmann solver-like class. But the interesting thing is that there is one parameter that you need actually from BBN, which is YP. And so really you need to pass that YP predicted to YP here before you can call the Boltzmann solver. In class, you have tables of YP as a function of omega B and N-effective for only two models, lambda CDM plus N-effective. And if you want to go beyond that, then you probably need to do something like this. All right. You have a CMB prediction from your Boltzmann solver. You have Planck measurements. You put everything into a Planck likelihood, you get L Planck over there. Okay, and then again, the same story. You do an MCMC, you get a posterior, you marginalize over all of the nuisance parameters. Okay. So why do you need LINX? So first of all, this is something I already said. You need to predict YP and pass it to CMB. In class, you can do this for lambda CDM and lambda CDM plus N-effective for the parthenopy rates. So even if you wanted to change the rates, it might already be a little bit difficult, I think, as far as I know. So that's one. Another thing also is that you need to kind of know that there are theory uncertainties associated with YP. One simplification that people used to people did, for example, in Planck 2018, is that they try to introduce the uncertainty associated with YP as like an additional factor in the likelihood that accounts for theoretical uncertainty. But if you do it this way, you don't actually need that. Okay, the LBBN itself knows about theory uncertainties. And then the last thing I want to say about LINX is that we've written it in a way that it solves everything faster than CMB Boltzmann codes. Yeah, go on. Yeah. Yeah, there's sigma ops, but then there are extra parameters which are your nuisance parameters, and then you do your MCMC over them, including them. Yeah. No. So exactly, we don't put in a theory error. This is what, for example, Planck 2018 do. I think the results are pretty good, but if you can do it this way, I think it's just better. And so yeah, we made it to be as fast as possible. I mean, compared to a Boltzmann code, a BBN solver isn't that much. So you really do want it to be much like at least faster than class, so that when you do a joint analysis, you're not being limited by the BBN code. Okay, so because of this, you can just kind of slot it into any CMB and BBN analysis, and you won't notice much of a difference. All right. Okay, so if we do the whole procedure that I talked about just now, there are roughly 40 parameters that you have to marginalize over. Over 40 parameters, a 40-dimensional posterior that you have to explore. There are 6 or 7 lambda CDM parameters, 13 nuclear rates, and 21 Planck nuisance parameters. And we do this with nested sampling in our paper. And then at the end of the day, you get nice 2D posteriors of, let's say, N-effective versus omega B H squared. All right? So I've already said this, which is that omega B with Fremont is roughly in 2 sigma tension with Planck. But it's nice that you can actually combine them, and you get a little bit of a tightening of the error bars as well when you combine all the information that you have, like especially in this case, which is the Fremont case. Okay, so that's one thing. So these are the results that you get just for N-effective, just for you to take a look. And so you get some shrinking of the posterior. Um, Another cool thing that you get from doing these kinds of combinations is that you can ask questions like, since Primart doesn't agree with the CMB at the 2 sigma level, what do I need to do in Primart with the Primart rates in order to get better agreement? And so, for example, you can see that each of these parameters controls the normalization of the sigma v, and you can see that in order for when you do a joint fit, the joint fit kind of pushes all of these rates by about 1 sigma to the left, and it has to be all 3 of the rates. It's not just one of them, and if you do the full analysis, you can actually narrow it down and see that it is actually these 3 rates that are the problem. You can also ask questions that Elizabeth mentioned previously, which is that you can compute things like base factors and stuff like that. Okay. So, okay, you can do this. Previously, people have done this for lambda CDM plus n effective, which is fine. And the reason that you could do these with these two is that these two models have been studied very extensively by the BBN community, so they can tell you, what is the theoretical error, for example, associated with predicting d over h and yp, and because of that, you can do a CMB analysis. But for other models, this is much harder because people have not studied other new physics models exhaustively, and so if you have a new physics model that you want to study a CMB BBN joint constraint, then really you need to do the calculation from scratch, and then this is where a tool like LINX will be helpful. Okay. One thing that I mentioned briefly is that LINX is written in JAX, which is a differentiable language. And the cool thing about differentiable languages is that whenever you write a function, you have the option of not just getting an evaluation. So for example, putting in these parameters, you can evaluate the likelihood. You have the option of also asking for the derivatives of the output as a function of the input parameters. This is cool because if you're able to obtain things like the gradient of the likelihood, then when we were talking about MCMC sampling, the way that we usually try to sample a posterior is to kind of take random steps in a random walk kind of way to explore this parameter space. But if your posterior is shaped in a very funny way where it's like narrow in one direction, then very often you will take a step and that step will lead to a lower likelihood and you get rejected. And so it takes a very long time to explore posteriors. But if you have these derivatives, then you can kind of think of the posterior space as an actual, like these contours are actually like valleys and peaks, and you can try to construct trajectories of your walkers through these like posteriors, and because of that, you can actually allow your samples to kind of explore things that are much further away, and this improves the efficiency of the Monte Carlo method. So this is something that's called Hamiltonian Monte Carlo, and you can do this if you have the gradient, and we demonstrated that you can indeed use LINX to do this kind of inference. All right? Yeah, go on. Yeah. Right, so for the BBN likelihood, it's very simple. It's just a Gaussian. You can't do it for the Planck likelihood currently, yeah. Uh, sh how does this work? So in practice, what you do is you write, you have the likelihood, right? So you put in these things, it goes through the solver, out comes the abundances, and then you match the abundances to the observed. That's your likelihood, right? And then if you write this function in JAX, it will also just give you these derivatives. Yeah. So any function has like inputs and outputs. You can ask JAX to also give you like the output, the input for any function. Yeah, and it will do it. It's not a numerical derivative. It's smarter than that. Okay. Any other questions? Okay, if not, then I invite you to take a look at the GitHub repository. There are a lot of dependencies, so there's no way you're going to install it and set it all up unless you already have Jax and a whole bunch of other stuff going. So I set up this nice Colab notebook, which thanks to an introduction from Misha and Elizabeth is really awesome. So you can just go to this URL, click it, and you can actually just run the notebook. The whole notebook will take maybe 5 to 10 minutes to run, but I have already run the notebook in advance. So after you open, sorry, did you get the, did I flash it for too short? It's tinyurl.com. Maybe I should just write it down. Just in case it gets lost, https tinyurl.com/ggi shram. Okay, and this Colab notebook will allow you to make a plot called the Schramm plot. And the Schramm plot is pretty straightforward. It's a plot of the elemental abundances as a function of baryon to photon ratio, including the uncertainties associated with nuclear rates. So at the end of the day, when you finish running this notebook, you will see a curve, which is like the abundance is a function of eta, and then this curve will have some which is the uncertainty associated with nuclear rates. All right, so if you take a look at this notebook, I'll just go through some of the main things and show you like some of the main capabilities. Let me just go to the GitHub, which is this one. It's cgiovannetti/LINX. cgiovannetti/LINX. And there are a bunch of example notebooks that you can go through. I'm just showing you one of them. If you want the Schramm notebook that you are seeing in the Colab, you need to go to the GGI tutorial branch. But then the structure is like what I showed you in the slides. And if you want to look at that plot again, you can look at some of the papers. Okay. So the first cell will just install all of the prereqs that you need to run LINX, which is things like Jax and so on. And then it imports a bunch of stuff, which is fine. And then the way that it works is you create a class, which is background model here, and then you call the class. And then you call the class. In this case, the only input that it needs, because so far Jax has only been written for lambda CDM and lambda CDM plus N effective. The only inputs that it needs, it just needs to know what delta N effective is for the thermodynamics part of the calculation. So their jnp.asArray just says that N effective is 0. You put it in, and then a bunch of vectors will come out, including the time, the scale factor, rho gamma, rho nu physics, which is essentially the delta N effective that you put in. In this case, if you put in 0, then it will be 0. The pressure, which is also 0 in this case, and then N effective as a function of time. Okay, so they're all of the same length, and you can just kind of stack them up. All right. Once you're done with the thermodynamics module, that computes all of the background quantities. And so now you have the background quantities. The next thing that you want to do is you want to build something called the abundance module, abundance model, which is another class. There you have a few networks that you can choose from. You can choose Premat as it was in 2018. 2023 is the latest update. And then you have Parthenopy and you have YOF. This YOF stands for Yeh, Olive, and Fields. And so it's a group that is based in Illinois and Minnesota that have their own ways of computing the reaction rates. Actually, I don't actually know if we are in 100% agreement with them on how to get the rates, but they do tell you where they got the rates from. So that's what we did. All right. So you choose one of them, and the whole syntax. You just call one of these things, and you create an abundance model. You can create your own nuclear network if you're an expert, but that's something that I won't show you. Okay, and then you run the code. Okay, so here you see um, abundance model will take in things like rho of gamma, rho nu physics, pressure of the extra species, Tvac, Avac, and eta fac, which just tells you what factor do I multiply the default value of eta by when I run the BBN code. And then at the end of the day, it spits out things like D over H, YP, and lithium 7 over H. Okay, so this should run in a minute, which may be a little bit alarming. It's just one evaluation. It runs in a minute. That seems like a very long time. But what's happening is that it's compiling. And then the second time you run it, it should run extremely quickly. Okay? So you run it a second time, and you see that it should take just a second or less. All right, so this time you see I can ask it to compute at a different value of eta, in this case 1.5. But because it's already compiled and you're calling the function in exactly the same way, it will just run the compiled function and you get these results very, very quickly. Okay, so that's the thing that we're leveraging from JAX. Another cool thing, like I said, is that you can get the gradient, right? So here, what I'm writing is a function that takes in eta fac, which is again the factor that you multiply the central value of eta by, and then at the end of the day, it will return the second entry, which is D, the abundance of deuterium. Okay, maybe in a more updated version, I set this to res 2 over res 1, which is D over H, but I made a mistake there. Anyway, so this is not actually D over H. I actually did, you need to divide by res 1 here, but it doesn't really matter. When you do it this way and you say at jax.value and grad, it will give you both the value, which is D over H, and then it will also give you the output over the input, which is this. Okay? And so if you change eta by 1, for example, so this is eta fac, not eta, but if you change eta fac by 1, it will cause this shift in D of H. All right? Again, you can see with the gradient, it takes much longer to compile. I'm not happy with this number, but to be honest, there are a lot of internal JAX things that I don't understand, that I would like to understand. But if this number can go down, I would really like that. And if any one of you is a JAX expert, I'd love to hear your thoughts. But anyway, at the end of the day, you can run the code in 7 seconds to get both the gradient and the central value. It's not great, but you don't actually need the gradient if you're just doing the regular random walk kind of MCMC. Okay? All right, so we can just make the Schramm plot. The first thing we'll do is to make it without any rate uncertainties. To making it with uncertainties is very straightforward. But here, what I'm going to do is I'm going to choose 50 points of omega b, running from 3 times 10 to the minus 3 to 6 times 10 to the minus 2, which is a huge variation. And then I'm going to define the same kind of function, which takes in a factor for eta, and then it spits out a list of numbers, which are the abundances. And then very importantly, I'm going to do something called VMAP, which allows me to change the input from just being a single float to an array of floats. Okay, so in the language of JAX, you basically, you code everything up, assuming everything is a scalar. And then at the end of the day, if you want to do a vectorization, you use this VMAP function to tell it how to vectorize all of your functions. So it's nice in that sense, like you don't really have to think about, sometimes you write a function and then you go like, well, okay, I actually want to vectorize this, and then you write another version of the function, things like that. You don't have to do that in JAX. And then JIT just tells it to compile. All right? So you run it again, you can get results. It takes 1 minute to compile again, and then subsequently it runs extremely quickly again. Okay, but you can make a plot, and this is the Schramm plot. And so for example, you can make a plot of yp as a function of eta, and that's the line in red. And then this orange bar here is the inferred value from the CMB, from Planck CMB. All right. So this is not really the full Schramm plot yet. This should be, you want the plot to not just have the line, but you also want to include the uncertainties associated with nuclear rates as well as the neutron decay lifetime, for example. So the way that you would do that is, again, you would write another function. This time, this function takes in 3 variables, a factor to correct eta, a factor to correct the neutron decay lifetime, and then nuclear rates Q controls the normalization of each of the nuclear rates. So nuclear rates Q should be an array of factors. So if you put nuclear rates Q to be 1, then it will just leave the nuclear rates at a central value, and if not, it will rescale the nuclear rates by some amount. It actually rescales the log of the nuclear rates. Those are just details, but just keep in mind that it just kind of shifts it around. Okay, and then we do the same thing. We VMAP it. We tell it that we want to pass an array of etas, and we want to pass arrays of tau and FAC and nuclear rates Q. Okay, and then we generate a bunch of random numbers for tau and FAC, so that corrects the neutron decay lifetime randomly, and we also do that for the nuclear rates, and we generate 25 different variations of tau n and the nuclear rates. So if you scroll up, you'll remember that I'm also trying to vary over omega b at like 20 different entries. Let me see, is it 20? No, 50 different entries. So the total number of evaluations that I'm going to do is 50 times 25, which is over 1,000 calculations. Okay. Again, you compile everything, you call it, it runs in just 2 minutes. Okay, and the compilation takes most of it. Okay, when you finally call it to do the 1,000 plus calculations, it's actually really fast. All right, so at the end of the day, after you pay the price of compilation, it goes really, really quickly, and then you can unpack all of the results, and then you can make the Schramm plot in the end, which looks something like this. Okay, so let me just go through it quickly. There is a thickness to the line, but the uncertainties are quite small, so you can't really see it. If I zoom in some more, you would probably be able to see it, but you can see it for lithium. Okay, so with the 12 reaction rates that we put in, the uncertainty is actually quite big, and you can see as a function of omega b h squared, this is the behavior of all of these abundances. In this is the in green is the CMB preferred value of omega b h squared at 95%, and then in yellow, which is not too easy to see here, that's where BBN tells you you should be. Okay, so if you look at the D over H, you can see a very thin yellow line there, and that's telling you that the BBN preferred range of omega b h squared is also very consistent with the CMB green line. All right, and then if you look over here, you will find that there is a disagreement for lithium-7 between what the CMB wants and what the BBN value for lithium-7 is, and that's the origin of the so-called lithium-7 problem. Okay, if they were in agreement, then this yellow box should overlap with the green box. Okay. So you can run this. One exercise that you can do is, instead of scanning over omega b h squared, you can scan over n effective. That would be fun. I've never actually seen that plot before. And then, yeah, there are 7 other notebooks that you can run if you download the GitHub. Yeah, I think that's pretty much all. Yeah. Mm-hmm. Yes. Sure. Yeah. I think I think changing G Fermi is the way that we do it. I think is equivalent to changing tau n. Yeah, because everything is normalized to tau n, and tau n is just proportional to G Fermi. So I think if yeah G Fermi squared. So I think if you change, it's just tau n. Yeah, but someone I think Niels Schoenberg asked us to do time varying electron mass, and that's harder. But I think we can do it. Yeah, so we're trying to do that. Yeah, yeah, yeah. Yes. Yeah, I at some point I coded it up halfway and then it got too annoying and I gave up. So it's halfway implemented, but I yes, if there's interest, I will definitely try to think about it. Yeah, 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 yeah. So okay, the way it works is okay. So let me explain the green line. This is just the 95% from Planck. That's easy. Second thing that you see is that all of these curves um, at each point, there are like 25 different draws of the reactions. And so that gives you some spread in the predicted abundance of lithium 7. Then what I do is, well, it's not me. I mean, what Schramm did was to say, okay, the observed abundance of, let's say, lithium 7 is this at 2 sigma. And so I know that that is consistent with this whole region of lithium 7 abundances. And so I can draw like a nice box like this, which tells me that this is the preferred value of omega B H squared, at least for lithium 7. Okay, and you can see that there's a huge discrepancy. For deuterium, it works much better because you can see there's a tiny little line there, which is the region, because the deuterium measurement is a 1% measurement. So in terms of like the height, it's very, very narrow. And then that like you imagine it's like a very narrow slit, and you kind of draw two horizontal lines across, and then the yellow box is where it cuts through the blue line, which is the prediction, including the uncertainties. And so BBN says that omega B H squared should be within this pink region at 95%. Okay, and you can see that the agreement is within 2 sigma. So this is the Premat. I use the Premat rates. You can use the Parthenopy ones where this two overlap would be better. Yeah. Yeah, exactly. Uh, I didn't actually do an inference here, but if I go back to how you would do it, you would have a 14D posterior that you want to sample, and then you have all these like points, and then at each point you have one of like 14 choices of all of these, and then you run the code once, and it will spit out the likelihood, and then you do MCMC with that. Yeah. Yeah. Thank you.